All right, but we are going to look at relativity uh, and a little bit about what Einstein did, because there is a, you know, like Einstein was the most brilliant person in the world, and what he does is inconceivable. Not always. In fact, special relativity, which is what we're going to spend most of the time on, is actually well within your grasp. General relativity, a little more complex. Now, relativity is not a new concept. We can go back and we can trace the idea of relativity to Galileo, basically. Back at the time of Galileo, there was basically two views of the universe. The one based on the works of Ptolemy, who was a Greek philosopher, Ptolemaic model, which is also known as the geocentric. It has the Earth at the center, the sun goes around it, all the planets go around it, and what they notice is that as they observe the motion of planets, especially like Mars, that it would undergo what was called retrograde motion. And typically, it would go across the sky from one side to another, but at certain times in the year, it would go backwards. And that didn't make any sense, and they tried to figure out how that was working. The Copernican model, which is after Copernicus, actually puts the sun at the center of the universe, and which is what we believe now. But the problem that they said was, okay, if the sun's at the center of the universe, the Earth must be moving around it. How come we don't feel it? How come we don't feel the Earth moving? Some of you would. I know, that's not even centered. And the answer is we shouldn't feel it moving. Because we're in what we call an inertial reference frame. If you imagine, back in the time of Galileo, let's say you were on a boat on a very calm day, and the boat was moving, and you were inside the boat, would you feel the boat moving if it was going at a constant speed? In our day, we would say, all right, we're riding in a car. If you're riding in a car on a nice smooth road and you close your eyes, do you feel yourself moving? No, not if you're going at a constant velocity. Now, if it were to accelerate, would you feel it? Brake, turn, speed up, yeah, then you feel it. But we're talking about at a constant speed. So Galileo came up with his relativity principle, and it's simply that all physical laws are the same in all inertial frames. So if you were traveling in a boat, on the inside of it, and you drop something, it would fall. It would be exactly the same. All the physical laws apply. Again, here's maybe some more modern day examples. Flying in a plane, you're flying at hundreds of miles an hour. You don't notice that. You notice if it starts to accelerate, but you don't notice it at a constant speed. Now, in the 1800s, a guy by the name James Clerk Maxwell, and this is going to be important, came along and he dealt with electromagnetism, EM, and he really proved that light was an electromagnetic wave and that it had a speed, 3 times 10 to the 8th meters per second. Now, at that time, what they didn't understand was, okay, if you've got a speed, it must be relative to something. We talked about that, way back when we started. If I move along the Earth at 30 miles an hour, the Earth is also rotating. It's going around the sun. So, do we judge our speed relative to the sun, or do we judge our speed relative to the Earth? So if we have a speed of light, it must be relative to something. And so what they did was they invented like a fabric of the universe that they called the ether. And the ether was always there, and that's what the speed of light was relative to. It's kind of the fabric of all the space. The trouble is, they could never prove that the ether ever existed. In fact, all the experiments that they did proved that it didn't exist. And so what was the speed of light relative to? In other words, what did we measure it to, according to? It was 3 times 10 to the 8th meters per second. How could we measure that speed if we don't know what it's measured against? Well, Einstein came along in the early 1900s, and Einstein had a new, really kind of a new way of approaching problems. He talked about as he would do Gedanken. Gedanken is a German word meaning thought experiment. He was not a very good experimentalist. He wasn't one to go in the lab. He was a theoretical physicist. He thought about things and then would prove them mathematically on paper, doing his different thought experiments. For an example, a question that fascinated him originally. If you could travel at the speed of light and you were next to a beam of light, what would you see if you're traveling at the same speed as it? Well, if we think, and then we'll get to that question, or that idea. If two phenomena are indistinguishable by experiments, then they are the same thing. In other words, well, he wasn't a good experimentalist. He knew that everything had to be proven by experiment. And if experiments prove two different things to be the same, you had to believe it. For example, if you take a coil of wire and you take that coil of wire and you shove it at a magnet, you'll get electricity produced. That's the whole idea behind an electrical generator. So you take a coil of wire, shove it at a magnet, you get electricity. Well, if you take a magnet and shove it at the coil of wire, you also get electricity. So are the two phenomena different? No, they're exactly the same thing. Basically what you need is you need motion, a conductor, motion, magnetic field, and you produce electricity. It doesn't matter which is moving relative to the other. They both produce a current. Here's this thought experiment. If you could travel next to a light wave, what would you see? Well, what would you see? What do you think? Now, if you stand and a car drives away from you, right, you see the back end of the car as it recedes into the distance, right? If you get in a car and drive along with it, what do you see? You look out the window and you see the other car, right? And if you're driving at the same speed, do you see the car moving? Not relative to you, right? You can still see it moving relative to the earth, maybe, but if you just look at the car, it's not moving relative to you. So if you're in a beam of light, if you're traveling at the speed of light, and you look at a beam of light beside you, what should you see? It'd still be a wave, but would the wave be moving? Think of it in a different wave. You're out on a lake. You anchored your boat, and you see the waves moving past you. Now you start to move your boat, pull up the anchor first, and you start to move your boat in the direction of the waves at the same speed. And you look at the waves, do they seem to be moving anymore? No. Well, and that was what he thought of. Get himself in a little car there. Now the problem is, the problem is Maxwell's equations that describe everything we know about electromagnetism says that you can't have a wave that doesn't move. So if it's not moving relative to him, it can't exist. These are the kind of thought experiments Einstein would do. So the problem exists is that the speed of light, if I move at the speed of light, it still has to be traveling at the speed of light. I have to observe it moving at the speed of light. This is one of the hardest concepts to accept in dealing with relativity. And that concept is The speed of light is a constant no matter how fast you're moving. And it's been proven in many, many experiments. It doesn't relate to our everyday experience. Because if you think about it, if you're in the back of a truck shining a flashlight, and the truck's moving forward, and as an observer in front of it, what should I see the speed of light be, according to common experience? If you're traveling at 50 miles an hour, and you're in the back of a truck, and you throw a baseball forward, and it leaves your hand at 50 miles an hour, how fast is the ball traveling according to the Earth? 100 miles an hour, right? Because just holding it in your hand, it's traveling at 50, right? And you throw it and it leaves your hand at 50, now it's should be traveling 100. That's why it's really hazardous to throw things at people out of a car. Because you got to add the speeds on there. Now, if we were to do the same thing with the speed of light, we would think that the speed of light would increase by 15 meters per second, which is the speed of the car. In reality, it doesn't. And that's a hard part for people to accept. It doesn't relate to everyday experience. And why not? Speed of light, traveling at the speed of light, doesn't relate to everyday experience either. We don't travel near that fast. It's impossible, as it turns out, to travel that fast, and we'll see why. So Einstein came up with two postulates. One, the relativity postulate, which is basically Galileo's. The laws, physical laws, apply in every reference frame. As long as they're an inertial reference frame, in other words, traveling at a constant velocity. Once you start to accelerate, things become different. And two, the speed of light is always the same no matter who is measuring it. And again, the relativity, as long as you're in an inertial frame, traveling at a constant rate, all of this is going to work. And that's why this is called the special theory of relativity, because it deals with the special case of having no acceleration. Once you try to include acceleration, then it becomes the general theory, because it involves everything. And it becomes a little bit more complicated. Now, what? Speed of light is constant, and the laws of physics apply no matter where you are. Those are the two postulates. Now, simultaneity, or whatever that is. Simultaneity, I can't say it. If things happen simultaneously, they happen at the same time, right? Now, here's a little bit of a problem for you. Let's say we've got a railroad car, or some kind of a railroad car that's enclosed. All right? In the middle of that railroad car is a light that flashes. It's right in the middle of the car. And you're traveling in that car, going down the road. It's all sealed, right? And the flash goes off. What can you say about the time it takes the light to reach the front of the car and the light to reach the back of the car? It should be the same, right? Because it's the same distance, you should have a simultaneous event. Correct? Everyone with me on this? Understand what I'm talking about? Now, let's say, so according to the observer inside the car, it's a simultaneous event. Now, someone sitting by the side of the road, watching it, they would see the flash go off, and as the flash goes off, the car keeps moving, right? That means the front of the car is getting away from the light wave as it approaches. And the one in the back is approaching it. So what will the observer by the side of the road see? He'll hit the back first and the front second. Is the event simultaneous to that person? No. Is it the same event being observed by two different people? So is it simultaneous or not? It depends on relative to what? It depends upon your point of observation. What this does, okay, now according to the guy, in the car, it's the same amount of time to go to front and back, right? Is it the same? And it's the same distance, right? Now, the guy on the outside of the car, does it take the same amount of time to reach the front and the back? No, it reaches the back first, right? Is it the same amount of distance? Speed of light's the same. So what must be different? Well, the distance was the same. They both traveled the same amount of distance. That didn't change. What changed is the amount of time that it took. And what this means is that is the amount of time that passes the same for the person on the car as it outside the car? No, it's different. And this is where Einstein's relativity starts to get kind of scary and kind of weird, is because time, we think of time as being something that's constant and the same everywhere. No, it's not. Time is relative. It's relative to how fast you're moving. Let's see if I can work my way through this and take you along with me. All right, that just says time. You read the article about time dilation before, right? Okay, we're going to go through it in detail because time dilation is a key to special relativity. What you have to imagine is you have a light clock. What is a light clock? Well, you take a certain you take a light source on the bottom and a mirror at the top. And then you send a pulse of light from the bottom to the top and back down again. And you measure the amount of time it takes to do that. Okay? We know the speed of light. How far does the light travel? Well, if the distance between the two is d, it travels a total distance of 2d. All right? And so we put that light clock inside of a spaceship with an astronaut. All right? And we let the clock move. Now, does it matter if the person on Earth is moving or the person in space is moving? Doesn't matter. It's relative to each other. So, again, on the spaceship, the beginning event A is when the light pulse leaves the bottom down here. The ending is when the light pulse is reflected back again. The amount of time that takes is 2 times the distance divided by the speed of light. How did I get that? Well, what is our equation for speed? Speed is distance over time. Solve that for time, and you end up with this. Distance over, it's basically the distance that it traveled over the speed that it traveled. It's the same thing. It's the same basic equation come up with Newton that we've been using so long. So that's the amount of time that Bob sees go by. Now here's where it gets weird. What does Sally see from the Earth as the spaceship goes by? If I go by you in a car and I'm throwing a ball up and down, I see a ball go up and down, right? What do you see? Ball going like this, right? Is that what you're going to come up with? Sally's going to see that be the path of the light. It's going to go up and down, but also across. Does Sally see it travel the same distance as Bob does? No, it's a lot greater distance. Now, if the speed of light is constant, and yet it travels a greater distance, what must be true about the time? It's got to be longer. It has to be longer. I'm going to throw a bunch of equations up here. I'm going to derive some of Einstein's equations, and I'm going to use algebra. Algebra that you could use at any point in time. And my point is, it's not that complicated. It's something that you can handle at this point. All right, so 2s. Okay, s is this distance right here. What have I formed right here? S, D, and L. I got a triangle, right? Now the total length that that light travels according to Sally is S and S, or 2S. Now, look at this down here. S, this side of my triangle, if I know L and D, I can solve for a Pythagorean theorem, right? S is the square root of L squared plus D squared. Correct? Pythagorean theorem. So 2S would be 2 times the square root of D squared plus L squared. Now we know that the change in time would be the total distance over the speed. That's right over here. So I can substitute that in for this distance right in here. For the speed I'm traveling, change in distance, time. Hey, come on. Get rid of that box. Come on. Oh. Now, to go from 2s equal to 2 square root of d squared plus vt over 2 squared, I substitute in delta t. 2s equals delta tc right here. I set then c delta t equal to this side right here. And by doing 3 algebraic steps, I end up right here. You want me to do the algebra? Say no. It's not that tough. If you want to see it, I can show you later. Now, according to Bob, this is the amount of time that he saw go by. 2d over c. Oh, look, 2d over c right there. Notice how it shows up in that equation. Simple substitution then. The change in time that Sally sees go by is equal to the change in time that Bob sees goes by, divided by this right down here, that square root, which is called a Lorentz transformation. This right here is called the gamma factor. It shows up in all the equations. 1 minus v squared over c squared. V is how fast the objects are moving relative to each other. Now, typically, we do not notice relativistic effects. Why not? Do we travel close to the speed of light? Not even a fraction. So if this is how fast you're traveling and this is fast the speed of light, if this is small compared to this, basically what does this become? This v squared over c squared. If v is small compared to c, it basically is 0, right? 1 minus 0 is 1. The square root of 1 is, so delta t that Sally sees is equal to what Bob sees. So the relativistic effects go away. But the closer we get to the speed of light, what happens to this value right here? It gets closer and closer to 1, right? 1 minus something close to 1 is going to be a value. The square root of it is going to be a number that's less than 1. Sally's going to see a lot more time go by than Bob. Now, I've said before, and you've heard other places, can you travel at the speed of light? No. Why not? This equation shows it to you right here. Which is this. The equation blows up. If you look at it in a calculus standpoint, the closer v becomes to c, the longer the time becomes. until as you reach v equals to c, you basically get to infinity. And you get infinite amount of time. So, well, Bob would see 1 second go by, or some unit of time go by. Sally would see an infinite amount of time. Can you have an infinite amount? No. The equations just blow up. If v were ever greater than c, now you've got a square root of a negative value, an imaginary number, and we don't work well with those. So going faster than the speed of light, the whole idea of time travel comes about because as you travel closer and closer to the speed of light, time differs. It basically goes slower for the person who's traveling because they see less time go by than the person on Earth. And so people would say the faster you go, the slower time goes. So if you go faster than the speed of light, you should go backwards. No, you don't go backwards. The equations just blow up. You can't be divided by zeros, and you can't be divided by negative square roots. That complicated, though? I mean, it's there. Is it conceivable? Could you work through it on your own? Maybe not. You got to be thinking about things in a really different way. Yeah, this is on the next test. Now, since time depends upon how fast you're moving, how then do we actually measure time? Well, the only thing that we can do is we talk about proper time. Proper time means as I look at my watch, I see 5 seconds go by. Let's say we go back to Bob and Sally. Sally looks at her watch and she sees 5 seconds go by. Bob's on the spaceship, he'll look at his watch and see 5 seconds go by. That 5 seconds means the same to both of them. But are the same amount of time relative to each other? No. Bob goes off, and he goes off on his space journey. Well, let's see. Let me skip ahead. This is called the twin paradox. Let's say Bob and Sally are twins. And we separate them at birth. We put Bob on his spaceship and ship him off. Leave Sally behind. Bob's going off to a distant planet, distant solar system, 20 light years away. All right? So he's 20 light years away. And Sally stays back. And he's traveling at 0.85 the speed of light. All right, so to write things down, Bob's speed is 0.85 the speed of light. Now, I'm not going to assign a value to that. I could take 3 times 10 to the 8th and multiply it by 0.85, but I'm not going to. And the distance that he's going to travel is 20 light years. 20 light years is a measure of distance. It's how far light travels in a year is a light year. So this is how far light travels in 20 years. So you take that time, multiply it times the speed of light, and you get an actual physical distance. But we're going to leave it as a light year because that's a little bit more convenient to use. Now, back to my time dilation equation. That one. So the amount of time that Bob sees go by, he's going to see how long is it going to take him to get there. Well, at 0.85, the speed of light, and the distance of 40, because he's going there and back, light years, 0.85 times 40 is how much? What? 37? Is it 37? Okay. So Bob sees 37 years go by. How much time does Sally see go by? So he leaves in his spaceship, goes there and back, comes back, he's 37 years old. Well, Sally, the amount of time that she sees Bob go by, Bob sees 37. Sally, 1 minus 0.85 over 34. Okay. All right, 0.85 C over C, so C cancels out. So we've got 34 over the square root of 0.15. How long is that? 34 divided by the square root of 0.15. $88 years. So Bob goes off on his little journey. He comes back and he's 37 years old. His twin, who was born at exactly the same time, is how old? 88 years in her time frame. Now, if he traveled faster than 0.85, what would happen to the difference in their ages? She'd be dead. Well, she might be at 87 too, or 88 or whatever it is. The faster you travel to the speed of light, the bigger the difference becomes. Yeah, they would look that old, and he'd get off. He'd be 37 years old, and she'd be in a nursing home somewhere. Even though this has been proven many times over. In the reading they talked about the whole GPS thing. If they don't correct for relativity on GPSs, after a day your GPS is off by, I can't remember, like 120 miles every day, because time travels slower for the satellite orbiting up there. Yeah, and sometimes I think that's other issues there. Yeah, just blame it on Einstein. They're not correcting for the relativity factors again. And the cop will just look at you and go, still a one-way street there, lady. Yeah. Now, okay, let's make things worse for you. If that doesn't match up with anything I got. Now, the relative speed that they each see is the same. Now, as I get in a car and I drive away at 50 miles an hour, you see me going away at 50 miles an hour, and I see you staying back there at 50 miles an hour. It's the same. We're same relative speed. Now, Bob if velocity is speed times time, right? Or no, is distance over time. All right? And if this is the distance that Bob travels, and he travels in this amount of time, and this is the amount of distance that she sees Bob travel in this amount of time, they have to be an equality. Does that make sense? Well, if Bob sees less time go by, what must be true about the amount of distance he sees go by? It has to be a smaller value in order for this ratio to work, right? If this is smaller than this has to be smaller than that in order to preserve the ratio. And so what that does is now we have length contraction also. He sees less distance go by. And if we extend that, if you go fast enough, things appear shorter and shorter and shorter. The theory was that if you went actually faster than speed of light, you'd actually see the back of your own head. Oh, that hurt. But you can't go faster than the speed of light, so it doesn't work that way. But everything does appear shorter to you because, again, the same amount, you're the same relative speed to each other. And if the amount of time you see go by is shorter, you must have experienced a shorter distance. Better yet, the faster you go, your mass changes. Your apparent mass. Now, does your mass actually change according to you? No, but someone observing you is going to see your mass getting larger and larger and larger, becoming infinitely massive. Because you're going faster. If you get to the speed of light, you would become infinitely massive again. Just like it becomes infinitely long. Isn't this all just fun to think about? Now, everything we've talked about has dealt with non-acceleration. I'm going to throw a little general relativity at you here because this is where it gets really mind-boggling. I knew you'd like it. Theory of general relativity came about because Einstein, we know about the orbit of Mercury. And the orbit of Mercury precesses a little bit. It's an elliptical orbit, and the ellipses shifts a little bit. And when they tried to predict how much it should shift, it wasn't right. It wouldn't fit according to Newtonian mechanics. And so Einstein started to change, came up with a theory of how things had to change. Now on Monday we're actually going to watch a video that talks about Einstein and his life and how general relativity, it took a while to prove. He came up with it as a theory, and it took like 15 years to prove it. It was a very, very long period of time, and it goes through all that. But if we think about it, if we're here on Earth, and you take a ball and you drop it, it falls, right? It follows a parabola. Now, let's say that you're in a car in space, traveling at a constant speed, where there's no gravity. And you drop a ball. What will it do? If you're traveling at a constant speed and there's no gravity, it'll just stay there. Okay, that's what they talk about, weightlessness in space. But let's say we take that car that's in the middle of space and we accelerate it. And we keep it accelerating. If I take a ball and I let go of it, it'll stay relative to space, but it'll end up in the bottom of the car, right? Because the car's, once I let go of it, it's going to accelerate. And the bottom of the car is going to catch up to it. So is there really a difference between accelerated motion and gravitational motion? No. It's really the same thing. It's going to have exactly the same effect. Now, have you ever seen a diagram like that? What Einstein said out of that was that space and time were actually a continuum, and there was a fabric of space that could be warped by density, by dense objects. And if you think of a ball rolling along here, a ball is going to follow the shortest line possible, but it's going to come along here, and that shortest line is going to pull it in to the center of that mass. Well, what does an object do when it reaches something that's got a gravitational pull? Same thing. It's actually following those lines. Now, okay, if we think of it in this terms, it's not so bad. You know, if you think about taking a ball and rolling it along, that object is going to end in the middle, right? But this is two-dimensional. Now think of it in 3 dimensions. I can't do it. People can. I can't do it. Now, if massive objects cause this warping of the space and the time, that means the closer you are to a massive object, the slower time moves. So if you want to live longer, then then you should live by something that's very, very massive. Standby crews, you'll live longer. Yeah, something was coming. Fortunately, there was someone bigger than me in here today, so.
That's why this class goes so slow.
Yeah, it's because I'm so big. Um, and it is something that they've proven. Actually, you know, they've taken clocks and things like that, and they put them near the pyramids of Egypt, very large objects, and time does slow down. You know, nothing you could ever notice, but it is slightly measurable. Um, a day equivalent to like a trillionth of a second. So in a trillion days, you're going to gain a second. Okay, it's not a lot. No. But it's just one of those more things you can think about late at night and keep you awake. Black holes are extremely dense objects that actually we think that time stops inside of black holes. The closer you get to it, it's being massive, time should slow down, eventually stop. Black holes are black holes because their gravitational attraction is so strong that light can't even escape it. There's an area called the Rothschild radius.
How is it even possible to prove that they exist? Because it was impossible to travel faster than the speed of thought. And if light can't get away from it, then nothing can. So
What the most common way of doing it is to look at galaxies, and galaxies should be moving in a straight line unless something interferes with it, right? But we'll see galaxies that are orbiting, nothing. And if you look at the rate they're orbiting, they must be orbiting something very, very massive, and that's a black hole. Because otherwise they'd be going in a straight line and we wouldn't be able to see that. There. That should be enough for one day, I would think. Now,